end, even if you do memorize this and you put yourself through hell to do it, then the final happens and there's no way you're going to be able to memorize all of it, right? It's better to learn it as you go. So, I'm going to say, let there be a perpendicular here, right? Totally valid. Vertex to 90. I can make an orthogonal whenever I want. So let, and I'll call it BD. And let it be perpendicular. That's the perpendicular symbol too, right? Perpendicular to ABC. Cool? Alright. So now that I've done that, I have two triangles, and if I prove them congruent, then I can get these two sides, and then by definition, that's an angle, a perpendicular bisector, right? Cool. So let's do that. I bet you see that this is also 90, right? And I bet you see that this is also a shared side, right? Just like before. So by shared side, BD, congruent to BD. And now we've got hypotenuse leg, right? AS doesn't work, but HL does, right? So by HL, triangle ABD is congruent to triangle CBD. And then we do CCP, and we get AB and CD together, right? So, by CCP, AB is congruent to BC. Therefore, by definition, D is on the perpendicular bisector of AC. You just proved that. Come in. Right?
That one was easy.
Some of these are. So don't focus on the easy ones. Focus on the hard ones, right? You're going to get the easy ones. All right. Proving perpendicular bisectors of something concurrent, right? So what we're going to do is we're going to use those two theorems, right, the converse and the regular, to prove that they're concurrent. So just a recap of what these are, right? If it's on the perpendicular bisector, then it's equidistant. And if it's equidistant, it's on the perpendicular bisector, right? So I'm going to draw some perpendicular bisectors. Totally valid, right, to draw on perpendicular bisectors. I just can't have them be perpendicular, a bisector, and go through a vertex, right? So what I do is I say, let that be the midpoint, right? And have this be the perpendicular bisector. Do I have enough room to actually make it perpendicular? I does, but it would go right through B almost. That's kind of annoying. That doesn't go through B, just so we're clear. It does not go through B, okay? Which is why I'm going to call this DE. Right? I'm going to do this for all of these, or at least two of them. So perpendicular bisectors go from midpoint up to 90, right? So I'm going to say let that be a midpoint. And then 90 from there is like this. And they intersect at some point, right? We know this to be true. They're not going to be parallel, no matter what you do. In order for perpendicular bisectors to be parallel, you would need a triangle that has two sides of it flat. That way the perpendicular bisectors run like this, right? So they're going to intersect at some point. Let's call that point K. So we're going to say let DKE be the perpendicular bisector. What side is DKE the perpendicular bisector of? What side is it perpendicular to?
Wait, DKE?
Yeah. What side is it perpendicular to? What side of the triangle is it perpendicular to?
Couldn't it be both? Because like it goes down both sides.
Well, one side of the triangle, I guess the big triangle, right? Mm-hmm. So this side right here, right? That's what's
I thought you were talking about the top and the bottom one, like CG or AFB.
Yeah, but even then it wouldn't be perpendicular here, right?
Yeah.
So it's here. So this is perpendicular to ADC. And then FKG is perpendicular to what side?
FKG?
Yep.
ADC. ABC?
FKG.
I don't know.
So that's why we need to talk about it. So
Oh,
FKG
AFB.
is perpendicular to this side, right?
Yeah.
Yeah, that's all. You know, be honest with yourself when you don't know, and then you can figure out stuff like that and go, oh yeah, that makes sense, right? Okay, cool. So they're perpendicular. Now, I'm going to prove that if I were to draw this last one in, like here, that it would also have to go through K. All right? And so the way I'm going to do that is this. I'm going to say, well, isn't K on a perpendicular bisector of this side? Right? Well, that means by perpendicular bisector theorem that it should be equidistant to the endpoints of the segment, right? You remember that? Right. So K should be equidistant to A. And it should be equidistant to B. So this is true. So AK is congruent to BK. Remember, it doesn't go through E, or this line doesn't go through B. Right? And this is all by perpendicular bisector theorem. Right? If it's on the perpendicular bisector, it's equidistant to the sides. Well, the endpoints, I should say. Well, isn't K also on this guy's perpendicular bisector, right? So it should be equidistant to C and A. Well, we already got the A, right? So it's going to be equidistant to C as well. Right? Now here's the beauty. We're going to use the converse now. Because according to this, right, I have the perpendicular bisector of this side. I have the perpendicular bisector of this side. The last one is what I'm going to talk about, has to go through K, right? So if you look, isn't K equidistant from C and E and C and B? That means it must be on this guy's perpendicular bisector, right? So if I were to draw it in, it would go through K. And I know that by perpendicular bisector theorem converse. K is on the perpendicular bisector of CD. So, K is on the perpendicular bisector of AB, this side, right? K is on the perpendicular bisector of AC, this side. And I just proved it's on the perpendicular bisector of CB. So it's on all the perpendicular bisectors, which means all of the perpendicular bisectors go through K, which means they're concurrent. By definition, the perpendicular bisectors of triangle ABC are concurrent. And we win. Proving concurrency, not that bad. It's really not. This one's the one that's kind of extreme, right? Because we have a lot of things. So remember what we're going to do is we're going to make this the medial triangle of a bigger triangle, right? Remember, medial triangles are when we have a triangle like this, and then we connect up the midpoints of this triangle. Right? When we connect the midpoints of a triangle up, it makes a triangle, this triangle, the one inside, right? And that's called the medial triangle. Because it's made of the mid segments of a triangle. Okay. So, we're going to use the converse of medial triangle theorem. Medial triangle theorem normally says that if you have a triangle and you connect its midpoints, then this will be half of this, right? This will be half of this, and this will be half of this, and opposite sides will be parallel, right? That's medial triangle theorem. Medial triangle theorem converse says that if you have a triangle, and then you draw another triangle around it by making parallels, if you make that, then that's a medial triangle. And if it's a medial triangle, you get all this crap, okay? So we're gonna say that ABC is a medial triangle of some other triangle, right? And we're gonna draw that triangle. So this is the hidden triangle inside, right? And we're gonna draw the triangle around it. The way we do that is just draw parallels, right? So what I'm gonna do is I'm going to draw a line that's parallel to this. Like this. Okay? So I'm going to say let this be parallel. I'm going to do a little parallel symbol here and here. Totally fine. Then I'm going to say let this be parallel to this guy. So I'm going to make the line parallel to AB. I'm going to put it over here. Okay? Still with me? Okay. Then I'm going to make a line that's parallel to this. Alright, I'm going to make it a little less than perfect, just to save on room. Alright. So these two intersect at some point up here. Are we cool with that? Right? I just ran out of room. Hi, Logan.
Who's the question? For this? Okay. Like, say this one. When I cancel out these.
If it's a fraction, is that the issue? Yeah.
Well, like, does this make, like, that 4 boxes? Like, do
It
I?
does, yeah. 4 boxes per person.
That's what's been thrown.
per 6 people, right? 4 boxes for every 6 people. It's gonna end up being a fraction, but that's okay.
Alright.
Alright, so now that I've drawn them, let's talk about like actually saying how to draw them. So I'm gonna call this point D and this E and this F. So we're gonna say let, and I'll try to squeeze it up here so you can see it all at once. Let me zoom in. So let this line exist, right? That's line FBE. Right? And what line is FBE parallel to?
AC.
Yep. And we also created line DCE, right? And we made that parallel to AB. And we created line DAF, and we made it parallel to BC, right? That's all, right? So first thing you do is you create your parallel lines to create your big triangle. And then by medial triangle theorem converse, we get all this congruency stuff, right? So next up is to say that's a medial triangle by medial, and I'm going to be super lenient on the naming of this because we proved this, but we never really gave it a name, and that's my bad. We get all this stuff. So we get that this side AC is half of the whole thing here, right? So I'm going to write that AC, whoops, let's do that in blue, is congruent to BE, is congruent to BF. With me on that? Right. I'm going to do the same thing for all my sides. So these guys. BC, congruent to AD, congruent to AF. Cool. And I'm going to keep going. I'm going to say that the pink sides are all congruent, right? AB, congruent to CD, congruent to CD. Right? Well, doesn't that by definition mean that C, B, and A are midpoints of my big triangle? Right? So when I draw my perpendicular bisectors, I'm going to go from there up to 90, okay? So now it's time to create our perpendicular bisectors. I'll do C first. Okay? So that looks like straight up 90. Now, before I go on, what's going to happen is that these are parallel and this is a transversal. So this and this are alternate interior, so they're both 90. So I'm going to do that. This is like the only time I recommend that you do it on the diagram and then write it, okay? Because when I create this, I'm gonna have letters, but there's gonna be a lot of connections, and I wanna make sure I get all those, okay? So I'm gonna do that, and I'll do it for every side. So that's gonna be 90. And if you look, these two are parallel, right? That's 90, so this is 90 by alternate interior, right? I would highly encourage you to do the ones inside the small triangle as empty colored, so you can match them up with the ones that are darker colored, okay? And then, we can match these up. And again, if I did this perfectly, they would all intersect at a point. So these two are parallel. So that means if this is 90, then this is 90 by alternate interior, right? So we're gonna say all those intersected at a nice point. I had to cheat a little bit, right? And we're gonna call that point K, or at least I am. That's what I usually do. So when I created these lines, I need C, I need K, and I need where it intersects with this side, okay? So I'm gonna call that CKG, because I've never done, I haven't done G yet, right? Also CKG is a thing, so. AKH, now H and I are the same sideways, right? So I don't like using H and I, so I go straight to J. If you wanna use H and I, that's fine. I just know people turn their paper a lot, and they're gonna get confused. And then I'm gonna do BK, it does go through K, I swear to God. BKL, okay? So now let's write all that. So I'm gonna go down here, I'm gonna say let CKG, let that be the perpendicular bisector of, what side is CKG the perpendicular bisector of?
My paper's so messy, I can't even see.
CKG is the perpendicular bisector of this side, right? See how it's perpendicular with it? Okay, so it's gonna go with DCE. Yeah, highly recommend colors, right? Then we know that the other perpendicular bisector I created was AKJ, right? And it's perpendicular to the green side. That's right, good job. All right, so I did CKJ, I did AKJ, or CKG and AKJ. Now I gotta do the one from B, right? So BKL. Notice all these have K in them, right? Because they're gonna be concurrent there. And BKL's perpendicular to what side? Yeah, the F isn't even on the screen.
EBF.
Yeah, very
or
good.
F.
EBF is alphabetical, but yeah. So, last thing is I'm going to highlight to you. Oh wait, alternate interior angles, right? That's how we got those 90s. So don't forget that. I always forget to write that because I do it on the thing before writing it. By alternate interior is that angle theorem. We know that this angle here, that's angle KCE. Are you smelling Stefan? KCE, this angle? Went with KGA, right? This guy. They're congruent. And BJBK, I'll do KBJ. This guy right here went with this one over here. That's AOK. Or KAL. Or KLA. KLA. Letters are hard. And then this guy, angle FAK, I'll do KAF, is congruent to this guy, CJK. Or if you want, KJC. I don't know, I like having the K first in this case. So, now the last bit of logic I have to show you is that, look, isn't this much of my perpendicular bisector an orthogonal? Right? It goes from vertex to 90. And this goes from vertex to 90, right? And this goes from vertex to 90. So by definition, AKJ CKG and BKL are orthogonals. Now, I'm not going to make you write that, but they are, right? By definition, those are orthogonals. Vertex to 90, vertex to 90, vertex to 90. And since they're just parts of these lines, right? Since the perpendicular bisectors intersect K, so do my orthogonals, right? So we're going to say, therefore, the orthogonals of triangle ABC, the original triangle, right, the OG, are concurrent. And that's it. That's like the main part of the package, right?
Okay, I have time for one more. Then I have to go.
Okay. So which one of these do you want to see? 11's really easy.
What are you just trying to do? Find the.
Well, it's the Mediacenter, right? So what kind of lines must these be?
I don't know.
Well, we have choices. Angle bisectors, perpendicular bisectors, medians, or orthogonals.
Oh, median.
They're medians, right? And medians are vertex to midpoint, so guess what? We get this for free, don't we? Like, I know you guys are really worried about these, but they're really not bad. You're going to want to have a lot of these on there. So, also, don't we know that the ratio of the medians is 2 to 1, right? So, big side, small side, right? So this would be half of 13. I don't care about that, but, right? And this would be double of 5, right? Big side, small side. So what's x going to be? 10, right? Like, you guys want these. You don't know it yet, but you do. This is the small side. Yeah, y is 13. Now, what do you notice? We have two 13s, right? Do you see that this giant triangle must be isosceles?
Yes.
Right? So this angle and this angle is the same. That's kind of fun, right? And these sides are the same. I don't know why I used dark blue again, but I did. Cool.
Wait, so wouldn't Z just be 20 then?
Yeah. Well, hold on. It'll be whatever these guys are, right? Put together,
Mm-hmm.
right? So we need to figure out what these are. Well,
Wait, didn't you say if it's 13, 5, and 12, then it like equals something?
yeah, it's a special right triangle.
Yeah.
Mhm. Yep, so those will both be 12, so this will be 24. These are both right triangles. Let me try to explain why that is. I made this very, very late. It might be missing some information. But you're right. It will be 12 and 12, which means Z is 24. On the test, I promise I won't have missing information.
Okay. We do 13.
You'd rather do 13, not 12?
Which one's harder?
12 has orthogonals, which means similar triangles, right?
Yeah.
So, I don't know, we can do 13. So check it out. How many triangles do you see in this diagram?
3. Small one, medium one,
Is that a
big
triangle?
one.
Is this a triangle?
No.
Nope, so just 2, right? If it helps, right? That's not bad. So we have 2 triangles in parallel lines. So guess what? We have similar triangles, right? Don't they share this angle? Right? And then by cap, these are the same, right? And you could also cap these as well if you wanted, right? These are similar triangles, is what I'm trying to say. So their sides should be proportional. So if you look, the side, the green and the blue side over here, right? That's 9 on the little triangle. It's going to be proportional to the green and the blue on the big guy. Now, how long is the green and the blue on the big guy? Be careful.
Is that green and blue? I can't
Yeah,
tell.
between green and blue, yeah.
12.
Yeah, 12. So 9 over 12 is the ratio, right? Now, similar triangles have proportional sides, right? So if that's 9 over 12, that relationship, right, which is 3/4, right? Then this side will also be 3/4. And this will also be 3/4. So which one do you want to go after first, X or Y? You want to go after Y. So on the small triangle, 12 is the base, right? And what's the base on the big triangle?
The base?
Well, the top part, right? I'm thinking the triangle's upside down.
Why?
Why? I asked the questions. All right, and you know how to solve a problem like that, right? I would advise flip both sides, so y is on top, right? And then multiply by 12 and win. Okay. I'll leave that.
Wait, so what about the x? What do you do with the x?
So, same thing, right? 9 over 12 will also equal whatever little guy's side is, x, right? Right? What's the big guy's side? Think segment addition postulate. What's the whole length here?
5 plus x.
Yes! I'm gonna write x plus 5. So here's how we're gonna solve this problem. I'm gonna multiply this over and get 9x plus 5 over 12 equals x, right? And I'm gonna multiply the 12 over. Does that make sense? Now you'll distribute and you'll solve, right? That's it. That's the hardest one I can give you for similar triangles. Like, you gotta be clever to be like, oh, that's x plus 5. I'm not afraid of that, right? That's it. Like, don't you feel better about these?
Yeah.
Right? I included them, and I know it's kind of unfair because I just gave you that homework assignment at the end. But I included them because I think if you know your crap from the more difficult stuff, these will be a breeze and should boost your grade.
Yeah.
So I'll keep recording even though you're not here, and I'll go over the rest of them, okay?
Okay. Thank you.
Yeah. So this guy would flip. And I would multiply by 12 to both sides, so I get 144 over 9 equals y. Don't simplify, don't care. Do not care. And then this is 9x plus 45 equals 12x. So when I subtract, I get 3x, and if I divide by 3, x is 15. So it turns out this is 15. And this is whatever 144 over 9 is. It actually does divide out, because this is 12 times 12, and this is 3 times 3. So I divide both these by 3, and I get 4 times 4, which is 16. So if you didn't have a calculator, you could do it that way. 12 divided by 3 is 4, 12 divided by 3 is 4, 4 times 4 is 16. And then this one. So we have similar triangles, right? Because vertical angles here. So these guys are similar. And not only that, but that's a right angle and that's a right angle. So these two triangles, both right triangles. That's a 3, 4, 5 right triangle. You could do p-theta to figure it out, or you could just know that 3, 4, 5 is a special right triangle, right? You do 3 squared plus b squared equals 5 squared. 5 squared is 25. Subtract 3 squared, which is 9. You get 16. Root of that is 4. This guy, since they're similar, right? We can match up sides. Green and red, right? 3 is going to go with 7. So on the small triangle 3, on the big triangle 7. And their relationship will be the same as the hypotenuse to this guy's hypotenuse. So 5 is hypotenuse is the small guy, x hypotenuse is the little guy. So flipping those, I get a much easier problem to solve, and then I times by 5 and I get 35 over 3 equals x. And that's not reducible, but that happens, right? It's totally fine. And then to get x, z and y, notice that these are both right triangles. And they share this angle A. So if you look, right triangle here shares the top angle, right triangle here shares the top angle. So by angle, they're similar. So this is similar to this. And by this, I mean not this piece, I mean the whole thing. So if you look, the hypotenuse here is 5. So hypotenuse on the little guy is 5. Hypotenuse on the big guy, be careful, there's the right angle, so this is the hypotenuse, is z plus 4. And that's going to equal, let's talk about this side, that's red to blue, right? That's a length of 12. So 12 for the big guy, and red to blue on this guy is 4. So red to blue on the little guy is 4, and red to blue on the big guy is 5 plus 12, or 5 plus 7, which is 12. So little guy's hypotenuse goes with big guy's hypotenuse, z plus 4. And big guy's red and blue, or sorry, little guy's red and blue, 4, goes with big guy's red and blue, 12. I would flip both to figure this out. If you want, you can reduce that and just call it 3, right? And we've got z plus 4 equals 15, which means z equals 11. So z is 11. Now same logic here, right? The base of the small guy will go with the base of the big guy, right? So 3 and y are going to go together. The same way that, I don't know, let's do the hypotenuse. 5 and 12 go together, right? Oops, sorry, not 5 and 12. 5 is the hypotenuse of this guy. The hypotenuse of this guy is 15. So you can be clever and be like, look, that's 1/3. What's 3 1/3 of? Well, it's 1/3 of 9. Or you could just be like, look, I'm going to flip this. Multiply by 3. And I get 9. So y is 9. So not the easy stuff, but definitely not the hard stuff we're going to do. Also not going to be a lot of the quiz. I might throw 2 on there at most. One more. So G is the circumcenter. And when is the circumcenter on the triangle? Well, when the triangle is a 90-degree triangle. So this must be 90. And remember, G is a circumcenter, which means there's a circle that goes around here. And these must be radii, because G is equidistant from here to here, right? And here to here. And here to here. So if that's 10, Z is 10. This is also 10. This is a right triangle. So you can do p-tag, 6 something and 10. So 6 squared plus x squared equals 10 squared. That's 36 and 100. When you subtract them, you get 64. So x, when you root that, would be 8. So x is 8. And if x is 8, notice that this triangle has a hypotenuse of 10 and a leg of 8. So this is going to be a leg of 6. So it turns out these two are the same. And if you look, if this is 6, right, this length is also going to be 6. So that's a 6 and that's a 10. And this is an 8. Notice we have another 6 and 10 right triangle. So that's going to be a leg of 8, which means the whole thing here is 16. The quiz will not have so many variables, right? I just don't like drawing these diagrams, so I tried to get a lot of different examples all into one. I'll probably give you like one variable to find out, and it won't be 12 different steps to figure out like how to get y or something. It'll be much simpler. Do your homework.